Welcome back. In this lecture, we are going to discuss the SciPy library in Python. So let's begin. So SciPy library is very useful and mostly used by the mathematicians for calculating differentiation, integration, interpolation, and linear algebra. So we are going to see how we can perform these operations using the SciPy library. So first I'm going to import NumPy as NP, import the matplot library for plotting different graphs, import SciPy as SP. Now from SciPy optimize library dot optimize, I'm going to import the minimize function that we are going to use in the next line. Alright, so here we have to minimize this function f of x equal to x minus 3 whole square. So we have to find the value at which this equation becomes 0. So we have to find the value of x. So we are going to use the minimize function. So first I'm going to define a function which will take x as input and it will return x minus 3 whole square. Alright, so now it is looking much better. Now this is the result. So I'm calling the minimize function and I'm going to give the initial value x0 equal to 2. And finally I'm going to print out the value of x. So here you can see the value is 2.99 and if we round off it will be 3. So if the value of x is 3, then this equation is 0. If I give the initial value x0 equal to 1, then you can notice the minor changes in the value. So here if I give 3, then it will return the exact value. Alright, so the next equation we have got is this, x minus 1 whole square plus y minus 2.5 whole square. And these are the inequalities, 3 inequalities. So we are going to define these 3 inequalities. This is the graph for this equation. So let me reduce the size. So these lines are touching the points here and we have to find the value of x and y for this equation. So I create a variable f equal to lambda, lambda is a function, and lambda x colon, and here I'm going to define the equation which is this one, this equation. Now I'm going to define the constraints. Constraints are these equations, inequality equations. So here I type type is inequality, comma, the function is lambda x colon, and here I define the equation. The next equation type again is inequality. And the function And the bounds value for both x and y. Now I'm going to use the minimize function, minimize f, and the initial value for both x and y will be 2 and 0, and the bounds will be b and ds, and the constraints. Now let's run this code. Alright, so I have missed the comma here. Now let's run, and here we got the output. So the value of x and y is 1.4 and 1.7. Now let's calculate the interpolation. So first I'm going to define the function. So the x will be the line space. So I use the NumPy library line space, and from 0 to 10 and the 10 values, and y will be the function x square sine x. And let's first plot the scatter x comma y. So now we have to calculate the interpolation. We have to find the values between these points. So we are going to perform the cubic interpolation that will draw a line between these points. So for this, first we have to import the interpolation library from the SciPy. So from SciPy dot interpolate import inter p1d. Now we are going to define f inter p1d x comma y comma the kind of this interpolation will be cubic. Extents will be the np dot line space from 0 to 10 and 100 values, and widens will be f extents. Now let's plot. So here we go. Now the points here are missing, so for this we will plot the scatter on this plot. And here we go. And if you want to see the number of values on this plot, so here I print the values of widens, and here we got all the values that are on this line. So let's move on and let's see for the differentiation how we can perform it. From SciPy dot misc, I'm going to import derivative. I'm going to define the function that will return x square multiply by numpy dot sine 2x multiply by numpy dot exponent minus x. So this is the equation of which we have to find the differentiation, and the x is, and here the x is numpy dot line space from 0 to 1 and the value 100. Alright, derivative, and the value of dx will be 1 exponent minus 6. So here we got an array of all the values for this derivative. Now let's see how we can plot this derivative. Now first I'm going to just plot the function f of x. So here plt.plot x comma f of x. So this is the function plot, and if we plot here the x comma derivative, where dx equal to 1 exponent minus 6, and here I'm going to plot the third one with n equal to 2. Here I'm going to turn on the grid, and here we go. So we have displayed 3 different plots for the derivative. Now let's move on and see how we can perform integration. So here we got the function. We have to integrate from limits 0 to 1 x squared sine 2x exponent minus x dx. So first we are going to import from scipy dot integrate. We are going to import quad function, a variable integrand equal to lambda x square multiply by numpy dot sine 2x multiply by exponent numpy dot exp exponent minus x. Now we are going to perform integration, so I create a variable integral, and integral error equal to quad integrand from 0 to 1. Now let's print out the integral and integral error. And here we got the result. Now let's perform this integration. Here we have double integration. So again we are going to import the integral function, which is the double quad. So first I'm going to import from scipy dot integrate, import double quad, integrand lambda y and x colon numpy dot sine x plus y square. Now here the first limit we have is the minus x to x square. So the lower limit lambda x equal to x colon minus x, and the upper limit x square. Integral and integral error equal to double quad integrand from 0 to 1, and the next limit is lower y and the upper y. Now let's print out integral and print integral error. And here we go. Now here we are going to solve the first order ODE, ordinary differential equation. So this is the air friction while falling. Now first I'm going to import the ODE function. So from scipy dot integrate, I'm going to import ODE int. Now here I'm going to define a function dv dt and the two inputs v and t, and return minus 5, and the initial value will be 0. Now the t will be the line space from 0 to 1 with 100 values, and the solution will be dv dt, comma the initial value v0 and the time axis, the t, which is the line space from 0 to 1. And here I'm going to create another variable, and I'm going to define the initial value dot t0. Finally we will plot the time axis and v, and here we go. So from the time axis from 0 to 1 we have plotted the function. Now we have the coupled first order ordinary differential equations. Here, letting s equal to y1 plus y2, we need to write the function that returns ds over dx equal to dy1 over dx and dy2 over dx. The function ds over dx can be taken as s equal to y1 plus y2. So first I am going to define the function ds dx, and here we will take s and x as input. Now y1 and y2 equal to s, and return y1 plus y2 square plus 3x. This is the equation we are going to define. 3y1 plus y2, 3 minus numpy dot cos x, y1 equal to 0 and y2 initial value equal to 0, and s0 equal to y10 and s and s0 equal to y10 and y20. X dot numpy line space from 0 to 1 ODEINT DS DX y1 sol and y2 sol equal to sol dot t initial value 0 plt dot plot x comma y1 sol and plot x comma y2 sol, and here we go. So we have plotted these two equations. Now we have the second order ODE. This is the equation of pendulum. Theta double differentiation minus sine theta equal to 0. So SciPy can only solve the coupled first order ODEs but any second order ODE can be turned into two coupled first order ODE. The same thing goes for higher order ODE. Define omega equal to d theta over dt so that one has the following coupled ODEs. So using the SciPy we can only calculate the first order, but if you want to go higher order then we can use the coupled ordinary differential equations. So first define the function ds dt as comma t, and here theta and omega equal to s, and return omega numpy dot sine theta pi by 4 and omega 0 equal to 0 as 0 equal to theta 0 comma omega 0. Now here I'm going to define the time axis numpy dot line space from 0 to 20 comma 100 sol equal to ODEINT ds dt and theta omega equal to sol dot t. Let's plot t and the theta. Alright, so now we are going to plot a time domain graph, then we are going to shift to frequency domain. So using the fast Fourier transform function. So first I'm going to plot a graph in the time domain. So here I create a variable x equal to numpy dot line space from 0 to 10 numpy dot pi and 100 values, y equal to numpy dot sine 2 np dot pi multiplied by x plus np dot sine 4 np dot pi multiply x plus 0.1 multiply np dot random dot rand n len x length of x plt dot plot x comma y. Alright, so here we got the sine function in the time domain. Now I'm going to shift this function, this output, in the frequency domain. So for this we have to use the fast Fourier transform. First I'm going to import the fast Fourier transform FFT from SciPy dot FFT import FFT comma FFT frequency n equal to length of y, yf equal to FFT y starting from initial value till the n variable which contains the length of y, and xf equal to FFT frequency np dot, and here the zeroth value, initial, the zeroth value, and here we are going to plot the xf comma np dot abs yf, and here we got the output. So this is the graph in the frequency domain. Now the last thing that we are going to do is we are going to solve the linear algebra. This is the matrix and we have to find the value of x1, x2, x3 and x4. So how we can solve this, let's see. So first I'm going to import from SciPy dot linear algebra module. I'm going to import solve triangular np dot array, and here I'm going to define the matrix. Now a new variable b equal to np dot array, and here I'm going to input the values of the column matrix 4, 2, 4 and 2. X equal to solve triangular a comma b and lower equal to true, and we are going to print the x. Alright, so here we have to also insert one more square bracket, and here we got the output. So we got the value of all the variables, all the 4 variables, and that's how you can use the SciPy library. I hope you have understood this lecture. If you have any questions, you may ask me in the comment section. So thanks for watching, and I see you in the next one.